I welcome you all in this presentation related with the subject fundamentals of surface engineering, and we are talking about the abrasive wear. We have talked about the mechanisms which are responsible for the material loss by the abrasive wear, and we have also talked about the summary of the different parameters that affect the abrasive wear behavior of a material. So, among the different parameters that affect the abrasive wear behavior, we have talked about the abrasive wear particles. So, just a quick look of the different factors that affect the abrasive wear behavior of the material includes like the abrasive wear characteristic, means which type of the abrasive will be causing the wear of the material due to the abrasion. So, it is the abrasive type and it is a relative hardness. Relative hardness it is with respect to the workpiece. It is with respect to the workpiece. So, as we have seen that since the different abrasives like alumina, silicon carbide and different particles will have the different hardnesses. So, according to the hardness of the abrasive particles with respect to the workpiece, the wear behavior is influenced in different ways as per the hardness of the abrasive. It has also been said that if the hardness of the abrasive is too high as compared to that of the hardness of the workpiece, then hardness of the abrasive does not affect the things much. But if the hardness of the abrasive is almost close to that of the hardness of the workpiece, then definitely it affects the abrasive wear behavior significantly. Now we will be taking up the other factors related with their effect on the abrasive wear behavior. So, the other factor is like abrasive grit size. Abrasive grit size. So, among the abrasive grit size, we know that if this is the surface of the workpiece which is under the influence of the abrasion and particle size is small, then under a given load conditions it will be causing a limited maximum up to the half of the diameter of the particle. So, maximum indentation which will be caused by the abrasive particle will be a smaller one, and under the abrasive wear conditions accordingly it will be forming the scratch of the same size along the length of the workpiece as per the abrasion until it is stopped or the scratching is stopped by the presence of the hard particles. On the other hand, if we consider that abrasive is of the larger size, and in that case under the service conditions which when the load is transferred through such kind of the particles, then it will be causing the larger size of the indentation which will be much deeper, and accordingly it will be developing the much larger size of the scratch. And since the volume of the material removed by the abrasion will be equal to the volume of the scratch which is being formed. So, the abrasive grit size directly affects the volume of the material being removed due to the scratching action, and if we see this closely, then the area of the material which is being removed from a particular section is being directly influenced by the depth up to which penetration is taking place by the depth up to which penetration is being caused by the abrasive particle. So, the penetration depth is small for the fine particle, while in case of the coarse particles the depth of penetration is more, and that is why what we see for the initial stages the wear directly increases with the abrasive grit size, especially under the low load conditions. Why it is about the low load, about that I will talk now. And the effect of the load on the wear rate with regard to the grit size we can see with respect to the abrasive material. Abrasive material itself, like few abrasive materials are very hard and brittle. So, these hard and brittle materials when they are subjected to the external loading, they have tendency to get fractured. They tend to get fractured into the fine pieces. So, even if the particle size is big, under the service conditions, if the hard brittle particle comes under the influence of external load, it will have tendency to get fractured. So, such kind of the fragmentation will be leading to the reduction in the size of the abrasives. So, if the load is limited, then the abrasive will be able to withstand, and if the load is high, then hard and brittle abrasives will get fractured. Now, this fracture can affect the abrasive wear in two ways. One is directly that the size of the abrasive is reduced, abrasive particle is reduced. Another side is that when brittle fracture of the abrasive particle takes place, it happens through the development of the sharp edges and corners. So, these sharp edged pieces of which are produced due to the fracture of the large size abrasive particles, these will have the sharp cutting edges, and these sharp cutting edges promote the removal of the material by the abrasion as well as the metal cutting. Basically, if the hard and brittle particles are there, and after the fracture it will produces the fine particles, although reduction in size should reduce the abrasive wear, but sometimes this is neutralized by the development of so many particles which are having the sharp cutting edges, which promotes the abrasion through the sharp cutting edges and removal of the material by cutting. So, the abrasive grit size has a different kind of effects in light of if we see as per the kind of material which is abrading. On the other hand, if the abrasive is tough and strong, in that case the abrasive particle, whether it is fine or the big one, it will not tend to break. So, no fracture in these cases or no easy fracture is observed, but the sharp edges, corners of such kind of the particles are subjected to attrition, which we can say gradual wear of the particles itself, and such kind of attrition leads to the rounding of particles which are hard and which are tough and strong, and such rounding of the abrasive particles reduces their cuttability, reduces their ability, their ability to cause abrasion. So, in case of the tough and strong abrasives, continuous attrition during the abrasion leads to the rounding of the abrasive particles, which in turn reduces their abradability or cuttability due to the reduction in the number of sharp corners, cutting edges, and so the cutting ability reduces. So, even if the particle is very large in size, but if it does not have sharp corners, then it will have tendency to cause more ploughing action rather than cutting or micro cracking. So, cutting will be more effective when there are sharp corners and edges are present in the material. So, what we can see here, the size in the size of abrasives in the beginning and the size of the abrasive which is actually acting onto the surface of the workpiece and causing the abrasion, these may be two different things, because as per the abrasive material, this size will keep on changing, the shape of the abrasive will also keep on changing. So, with regard to the size, if we see the size effect, so on increasing the size of the abrasive, say 100, 200, 300, 400, 500 micrometer average diameter of the abrasive, then initially it rapidly increases the wear of the material, and then rate at which the wear of the material will be increasing with the increase of the abrasive size, that will be reducing. However, this rate may vary for the different material. This may be for one material, material A, then for the material B it may change like this, for material C it may change like this. So, initially there is a sharp increase in the wear with the increase of the abrasive size, and thereafter the rate of increase in the wear decreases with the further increase of the abrasive. So, this what we may see after some time, after initial fast increase there may be flattening, wherein means for the larger size abrasives may not be able to increase the wear further, but wear will keep on taking place at a particular rate only. So, what we will see here, and what is the reason behind this? When the abrasive size is small, it has less tendency to get fractured as compared to the case when the abrasive particle size is large. Large abrasive particles will start getting fractured. So, after certain stage when it happens, then say for this particular plot, beyond this size means above this size of the abrasives, the further increase in size of the abrasive will lead to the situation where under the given surface conditions abrasive may start getting fractured. So, the size will start getting reduced. So, the abrasive increase in abrasive size increases the wear up to a certain critical level. Thereafter, there may not be a significant increase in the wear with the increase of the abrasive size. Abrasive shape is the another aspect, the shape is like the angular abrasives, which may be like in form of the sharp corners or sharp edges. These will be causing the higher wear rate, higher abrasive wear as compared to the round shape particles, and round shape particles will be causing the lesser wear due to the absence of the sharp cutting edges. So, in these cases mostly the material loss takes place by the ploughing action. The other factors like the speed, load, specimen size and the wear track. So, if we see abrasive wear means like say the speed at which the abrasive medium is moving over the surface of the workpiece. So, it may move at like say 0.1 meter or it may move 2 meter per second. So, when the abrasive is moving at the different speeds with respect to the workpiece, so accordingly the material present at the surface will be affected by the deformation or by the work hardening, because whenever the abrasive load is applied through the abrasives, material will be deformed plastically, plastic deformation, and which in turn will be experiencing the work hardening. So, near surface layers will always be experiencing the deformation as well as work hardening. So, work hardened material will have its own effect. Whenever there is a change in the speed, then the rate of the deformation of the material is affected. If we tend to deform the material at a higher rate, then it tends to behave more like a brittle material, low ductility. This is what we can see from one simple diagram also, like during the tensile test, if we perform the tensile test at low strain rate, then we may find one plot like this, say at 0.1, which is basically about the cross head speed 0.1 mm per minute, and if we do it at 1 mm per minute, then we may find with higher yield strength and higher ultimate strength and lower ductility in terms of the percentage elongation. So, this side we have a stress and this side we have a strain. So, higher strain rate tends to increase the yield strength, hardness and reduces the ductility. Similar kind of the experience will be, similar kind of the behavior will be shown by the material present at the surface when it is subjected to the abrasion by the particles moving at a different speeds. So, at low speed, so this is one aspect, that the strain rate experienced by the material with the variation of the abrasive speed, that will be different. Another aspect is whatever work is done during the interaction of the abrasive particles with the workpiece, a part of that work is converted into heat. So, when we move the abrasive at a higher speed, so more heat localization will be taking place, which in turn will be increasing the temperature of the workpiece surface layer. So, there may not be, although during the abrasion there may not be very high temperature rise may be like 2 degree, 3 degree, 5 degree or 10 degree, most of the time it is not much, while in case of the adhesive wear the rise in temperature is significant, it may be like 100, 150 or even 200 degree centigrade rise in temperature can occur under the adhesive wear conditions. So, these are the basically two factors, two factors which affect the abrasive wear with the change of the speed. So, if we put the speed of the abrasive movement like 0.2 and here if we have 2.0 and this is the speed of the abrasive movement and here we have the wear rate, then this is found almost constant or there is a very marginal increase. So, this slope is very less. So, which suggests that there is no major change in the wear rate, abrasive wear rate with the change of the speed of the abrasive or the speed at which the abrasive action is taking place, and whatever minor increase in the abrasive wear rate is occurring, that is basically attributed to the increase in temperature due to the heat generation or localization of the heat generated, which will be leading to the minor reduction in the hardness. And second one, which will the factor which will be acting in opposite way, that increasing increase in speed will be leading to the increased strain rate which will be experienced by the material during the deformation or during the interaction of the abrasive particles with the surface material. So, this will be causing the increase in the hardness of the material. So, these two factors may neutralize, that is why we do not generally find a significant change in the wear rate with the increase of the speed. The another important factor is the load. Initially now we know that this is the surface of the workpiece and abrasive load is applied through the abrasive onto the surface of the workpiece. Under these conditions, what will happen is increase in load, and under the identical condition if the abrasive retains its size and shape, then increase in load will increase the depth of indentation. So, increasing depth of indentation will simply increase the abrasive wear rate under the identical condition. But if with the increase of the load abrasive starts getting fractured, getting damaged, then the increase in the abrasive wear rate will be reduced. Here we have the abrasive wear rate, which we say in terms of like the loss in terms of like mm cube per meter or per unit time. So, if we plot that, then with the increase of the load there is a continuous increase in the abrasive wear rate up to a limit. Thereafter, it will start getting flattened. So, there may not be much increase. So, there is a direct relationship, means the wear rate initially proportional to the load, but up to a limit. Thereafter, deviation in the increase in wear rate and load relationship is observed, and the curve starts getting flattening. This is the condition which suggests that the damage to the workpiece, damage to the abrasives have started, and simply increase in the load is not causing much of the indentation to cause the cutting and abrasive action, and that is why increase in load increases the abrasive wear rate up to a certain limit. Thereafter, further increase in the load does not increase the abrasive wear rate appreciably. The another important factor is the like the wear track length. For example, under the identical condition, if this is the sample and if we apply the abrasive and then cause the abrasive action up to this length, then it will be causing the weight loss is W1 or wear volume is the W1. And if this distance is linearly distance is doubled, then what we will see that it is the twice of the initial weight loss in the first stage or twice of the volume loss which had taken place in the track 1 and this is track 2. So, track 1 means when the abrasive interacts with the workpiece up to certain distance, say it is 100 meter, and so we get the weight loss W1, and when this distance is doubled to 200 meter, then we will find means for another 100 meter distance. So, the total distance traveled will be 200 meter, and then again we measure the loss. Then for the another 100 meter interaction of the abrasive with the workpiece, again it will be of the same magnitude. So, if we check the total loss of the material, then it will be twice of the W1 or twice of the V1, and that is why normally as we increase the sliding distance or the length of the wear track under the abrasive wear condition, that it linearly increases the wear abrasive wear, which is in terms of mm cube. And if we measure the wear rate where mm cube per meter sliding distance, then there may not be any change in the wear rate as a function of distance, it remains almost constant. So, this is about the effect of the wear length. These are the other factors like the mechanical properties and the effect of mechanical properties and frictional heating and humidity. As far as the frictional heating and humidity is concerned, what we will notice that if the abrasives interacting with the workpiece in the humid environment, and this humid environment is causing the chemical action with the surface of workpiece, which are and whatever chemical compounds being formed at the surface, if they are soft and can easily be abraded, then such kind of the abrasive action onto the chemical compounds being formed in presence of the humid environment, then it will be increasing the wear rate. So, as compared to the dry environment, humid environment will be causing the greater abrasive wear rate if it is interacting with the workpiece surface and forming some of the soft compounds. On the other hand, if the frictional heating is too much, then it will be leading to the rise in temperature of the surface of workpiece, which will be softening the workpiece material and increasing the indentation depth by the abrasives, and which in turn will be increasing the wear abrasive wear of the material. Similarly, effect of the hardness, we have already talked of bulk hardness or surface hardness of the work piece. There is a difference in the bulk hardness and surface hardness in the sense that if this is the surface, so distance from the surface is like surface, this is 1 mm, 2 mm, 3 mm, 4 mm, increasing depth from the surface. Then what we will notice, the surface which has been subjected to the abrasion, it will have the higher hardness, because the surfaces experience the deformation and which will be causing the work hardening. So, the surface and near surface layers have the higher hardness as compared to the subsurface region. So, this is the distance up to which say work hardening effect can be noticed, and below that there is a subsurface region where there is no change in the hardness, no change in hardness due to the surface layer deformation. So, this is basically the bulk hardness. What matters in the abrasive wear or in all kinds all forms of the wear is what are the actual surface properties, and these surface properties are actually modified during the abrasion or during the adhesion or erosion. So, we are more concerned about the surface properties, which are usually higher due to the surface layer deformation under the actual service conditions like in abrasion, adhesion, etc. Another important property is the flow characteristic or fracture characteristic. For fracture characteristics, like we have fracture toughness of the material. So, fracture toughness shows the resistance to the crack growth and resistance to the fracture by the crack growth. So, if the K1C of the material, means the fracture toughness of the material is high, initially it increases the fracture toughness significantly, and thereafter it starts getting flattening. So, abrasive wear behavior of the material can be compared, and we may notice that for as the fracture toughness of the material increases, in general resistance to the abrasive wear resistance, basically abrasive wear resistance increases with the increase of fracture toughness, thereafter it starts getting flattening. Similarly, the flow characteristics of the material, it is not just the yield strength of the material. If the material is under the annealed condition, then flow stress and yield stress both are same, but if the material has been subjected to some kind of the deformation effect either during the service or it has experienced the work hardening effect, then we need to consider the flow stress, because flow stress decides the sidewise flow of the material under the influence of the abrasion or under the influence of the abrasives. So, which will be responsible for determining the depth of penetration by abrasives. So, if the flow stress of the material is increased, then of course, it will be reducing the abrasive wear certainly up to some extent, but a significant increase in the flow stress means material will tend to behave like a brittle material also. So, too high flow stress means the material in that case will be of very high yield strength, in that case it will be losing its ductility, hardness will be increasing. So, that may again that situation may not be favorable, and the abrasive wear may start increasing, especially under the impact conditions. Now, the another important aspect is the factor which will be affecting the abrasive wear is the metallurgical aspect. We know that the metallurgical properties significantly affect the mechanical properties like hardness, flow stress, fracture toughness, and therefore, it is important that the metallurgical efforts are made to relate the metallurgical properties with the mechanical properties and then their tribological properties. So, as far as the metallurgical properties are concerned, we need to consider the phase structure, means what are the different phases, what are the different types of phases which are present, what is their relative amount of the different phases. Like the matrix is aluminum and the 20% is of the silicon carbide. If this is so, this is the matrix one phase and this is the another phase. Similarly, we may have the 80% of the perlite and 20% of the cementite, Fe3C. So, these are the two phases, the type of phase perlite and cementite, and what is the relative amount or proportion of these phases. So, increasing percentage of hard phases in general increases the abrasive wear resistance, and therefore, efforts are made especially in case of the soft matrices to reinforce the hard particles, so that their abrasive wear resistance can be enhanced. So, soft materials like soft metal matrix like iron, aluminum, cobalt, nickel, these are soft and comparatively tough. So, efforts are made to reinforce some hard particles in the matrix of the soft particles, so that their resistance to the abrasion can be enhanced, and it can be in form of like reinforcement of Al2O3, silicon carbide, tungsten carbide, etc., as per the purpose and compatibility. So, in general, if we see as far as the type of phase is concerned, in case of the simple iron carbon system, increasing percentage of the carbon like 1, 2, 3, etc. So, the increasing this will be increasing, say, the fraction of the cementite. So, cementite on the x axis, if we have like 12, 24, 28% of the cementite in the x axis, and in the y axis what we have, the abrasive wear. then what we will notice that there is a continuous drop in the abrasive wear with the increasing fraction of the cementite, because as compared to the perlite, cementite, perlite and ferrite, cementite Fe3C is harder, significantly harder. So, which in turn resists the abrasion through by reducing the indentation, and therefore, abrasive wear resistance is enhanced with the increasing fraction of the cementite. And similar kind of the studies can be undertaken for a varying fraction of the different hard constituents being reinforced in the soft and tough matrix. Similarly, apart from the fraction of the hard phases being reinforced in the soft and tough matrix, it is important that not just the fraction is important, but how they are distributed and what is their size. So, just big size particles may not be enough. It is always good that particles are small in size and they are well distributed. This will help in two ways. So, what is important, that fine particles and well distributed particles, so that inter particle distance is less to cause the abrasion. If the abrasion is being caused, then the soft matrix will be abraded in this case, and then the path of the abrasion or the scratching action will be stopped by these hard particles. But if the abrasives are widely spaced, then the abrasion will be taking place very easily. So, in order to have the good abrasive wear resistance, it is important that particle size is fine and it is well distributed. However, the exact size of the particles to be reinforced will be determined by the size of the abrasives that will be causing the abrasion under the actual service conditions. So, considering the services, the type of abrasive size must be considered for designing the surfaces, so that we can have the constituents of the suitable kind and of the suitable size at the surface layer, so that it can offer the required abrasive wear resistance. Now, here I will summarize this presentation. In this presentation, basically I have talked about certain factors like the abrasive properties, the service conditions like load, the speed, and the metallurgical factors like the phase and grain structure and the way by which they affect the abrasive wear behavior of the material. Thank you for your attention.